Hello there. So last time we were talking about when do you use implicit differentiation, and we talked about two cases, mainly where we need to use implicit differentiation. That is when the dependent variable is not linear. So you see y of a higher order, y squared, y cubed. And the other case is when we cannot neatly separate the dependent from the independent variables. So that's when we cannot put all the dependent variables on one side of an equation and all the independent variables on another side of the equation. This time we are going to see more examples of using the implicit differentiation technique. So let's get started. You will see in this example that obviously we are going to do implicit differentiation because we see that the dependent variable y is of the third order. You have a y cube. So automatically you will get 2x cubed. We derive this like we always do. So we just use the power rule. This is 6x squared. And then when you reach 3y cubed, you derive this the usual way, which is again use the power rule. This is 9y squared. However, by the chain rule, you know that this y has a derivative, which we do not know as of now. So we just say times that derivative of y with respect to the variable of differentiation x is equal to, and then you have the derivative of a constant that's just 0. Now, what's up next? We try to isolate dy dx, or the derivative, from everything else. And I think it's this is quite easy. This becomes 9y squared times dy dx is equal to negative 6x squared. And finally, you have dy dx. Our isolation is successful. This is negative 6x squared all over 9y squared. Or to simplify, this is negative 2x squared all over 3y squared. Sir, is it all right if after the implicit differentiation I arrive at an expression for the derivative which has a combination of x's and y's? Just like in this case, you have in your numerator 2x squared, but in your denominator you have 3y squared. Well, when you're doing implicit differentiation, it's totally acceptable. All right, so you can already box this as your final answer. This is 2x squared all over 3y squared, and you're good. Okay, shall we have another example? Here we have a combination of reasons why we need to do implicit differentiation. To begin with, you have the dependent variable not in the first order. You have a non-linear dependent variable in the form of y squared. And to add to that, the second term, negative xy, is not variable separable. This means that you cannot rewrite this. There is no way for you to rewrite this in a way where only one side of the equation has y's and the other side of the equation has x's. They will always come in many ways, in many forms. You will always see an x and a y together. So all the more here, you need to do implicit differentiation. So let's do that. You have here, not to worry, x squared. We've done this so many times before. The derivative of x squared is 2x. Now you have a product of x and y. So here you have to do the product rule. So the product rule says that the derivative of the first function, x, is 1, so we don't write that anymore, times the second function, y, plus the first function, times the derivative of the second function. So we have y here. So the derivative of y is, for now, we just write it as dy dx. We do not know what exactly is it, but for now we write it as dy dx. And then plus you have here the derivative of y squared will be power rule, so 2y, but then we know that y by chain rule has a derivative, so we multiply that with dy dx is equal to the derivative of 7, that's 0. So shall we further simplify this? And so you will have here, see, 2x minus y minus x dy dx plus 2y dy dx equals 0. And then we try to put on the other side those terms that has no dy dx's. So you will get y minus 2x is equal to 2y dy dx minus x dy dx. I hope you could follow. And then we are trying to isolate dy dx from everything else. We can do factoring here. So we factor out dy dx is rather times 2y minus x is equal to y minus 2x. And we're very lucky. We can finish off this isolation. Dy dx is equal to y minus 2x all over 2y minus x. With this, we can already box this as our final answer. Okay, and we are able to arrive at the derivative only through implicit differentiation. Shall we see another example? Again, I am seeing a combination of reasons why we need to do implicit differentiation here. One, sir, I see that a term has the dependent variable of a second order. It means, sir, I'm seeing a y squared. Correct. Also, sir, I am seeing that I cannot separate the x from the y in this expression. So I cannot put on one side all the x's and on one side all the y's. So this tells me I need to do implicit differentiation. You're correct. So shall we do that? We need to do product rule for x squared y. How? So the derivative of the first function, here in this case x squared, so the derivative of x squared is 2x times the second function y. By product rule, we need to add there. Now, the first function, x squared, times the derivative of the second function. So the derivative of y, sir, is for now dy dx. I do not know what that is, but for now, I just write it as dy dx. Okay. Plus, now, on the second term, we need also to use the product rule. So we have, again, the derivative of the first function, x, so that's 1. Very good. You don't need to write that anymore. Times the second function, y squared, plus the first function, x, times the derivative of the second function. So what's the derivative of y squared? So by power rule, that is 2y. And then by chain rule, I know, sir, that y has a derivative. I don't know what it is for now, so let's just write that as dy dx. Right, good. So here, I'd just like you to take notice that we apply the product rule twice. We apply the product rule. By the way, baguhin ko lang yung arrow. Baka malito kayo. Okay, so the product rule on here and the product rule also on that term. Good. To continue, is equal to the derivative of -2, since -2 is just a constant, so the derivative of that is 0. All right, shall we continue? What's the next step? So the next step is I will try to isolate the dy dx's from everything else. Correct. Okay, so let's rewrite this. Let's rewrite this is 2xy plus x squared dy dx plus y squared plus 2xy dy dx is equal to 0. And then I try to put everything that doesn't have dy dx's on one side. So I have here, sir, negative y squared minus 2xy. And on this side, we have x squared dy dx plus 2xy dy dx. Okay, so far so good. I hope you can still follow. And then we factor out dy dx. And we are left with x squared plus 2xy is equal to negative y squared minus 2xy. And to finish this off, we have dy over dx is equal to negative y squared minus 2xy all over x squared plus 2xy. Or this is negative of y squared plus 2xy all over x squared plus 2xy. So I hope you don't have any more questions. We'll see more examples of implicit differentiation, this time when we have transcendental functions in the next video. So see you there.